sub-Saharan Africa, right? So that is so that you really have to understand the distinction between risk factors versus causal factors. In this example, for example, the risk factor here is living in sub-Saharan Africa, and that is simply a proxy for a whole lot of things like malnutrition and poverty and so on and so forth. So again, this is going back to our our critique of Koch's postulates that it's not always very easy for us to identify one clean exposure that is killing people, right? Because there could be many, many, many things at play that is impossible for us to cleanly identify each one of them individually. And that is why in epidemiology, we use risk factors a lot as opposed to just causal factors, because in the first place, it's almost very hard for us to measure those causal factors anyway. And that's why risk factors become very important in epidemiology overall. All right, so now let's talk about the second framework. So the first framework we've discussed so far is Koch's postulates. And we've talked about some of the limitations with Koch's postulates, that essentially you can always pinpoint the exact causal factor. And at best, what we have are risk factors. We've also said that another problem is that you have the issue of baseline risk. Even people who have never been exposed, especially for chronic diseases, can still have that outcome. And so those are some of the issues with Koch's postulates. Another framework we use a lot is Hill's criteria. Bradford Hill was a British scientist, epidemiologist, and he came up with this criteria, this list of factors to say that let us, when we want to explore causality, let's think of these things all together. And then let's take the evidence and say, okay, when we consider everything, is there evidence that this is a cause of that? And these are the things that he mentioned: experiments, temporality, biologic gradient, strength of association, coherence, consistency, specificity, analogy, and plausibility. This is my own arrangement of these factors. This is my own personal, way of arranging them from the most powerful to the least powerful. I start from experiment because if there's an experiment, then obviously experiment also includes elements of temporality. Temporality simply means that the exposure came before the outcome, right? So we know that Mary took the pill first and then she died. So the exposure came before the outcome. That's what temporality is. Experiment simply means that we can conduct experiments where we assign people to different things. Like we can assign some people to taking the pill and some people to not taking the pill, and we can see their death rates in the two groups, right? I put a red star here because in the real world, it's not everything that we can do an experiment on, right? Things that are obviously harmful, we cannot subject people to experiments. And sometimes you really don't need an experiment. For example, you don't need an experiment to tell you that, oh, if you get hit by a train, you're going to die. I don't think it's completely unnecessary for someone to say, okay, let's randomize people, right? Half of them will be put in front of a train and the other will not. So experiments are not necessary in some cases where there's obvious harm. And so that's why I put that in asterisk there. Temporality is important because for us to make claims of causality, it is clear that the exposure should come before the outcome. If the outcome comes before the exposure, then we call that reverse causality, because it's, the thing happened first and then we're trying to look for a possible explanation. And so we don't want that, obviously. Biologic gradient means that there is a dose response. So that means that if I am saying that there's a relationship between smoking and lung cancer, I expect to see that the more cigarettes you smoke, the more your risk of lung cancer. Or if I'm saying that there's a relationship between eating sandwiches or drinking, Coca-Cola or soft drinks and obesity, I will expect that the more drinks you take, the more obese you are. So there is a dose-response relationship. And that's why, for those of you who are doing your thesis or dissertation, that is why it's always a good practice to have more than just two categories for your exposure. So if you are looking at smoking, for example, it is more interesting to look at multiple categories of smoking than just simply dichotomizing it as smoker or non-smoker. Because if you just have two categories, you obviously cannot examine a dose response in that kind of context. The strength of association is telling us how big is the odds ratio from your analysis. In general, if you have an odds ratio of, for example, 3.0, that's a very strong odds ratio, right? As opposed to an odds ratio of like 1.01, that is rather weak. So the strength of association is telling us how big is the measure of association from your analysis. Coherence is simply saying, when we say coherence in English language, it means that there is a flow, right? Coherence is the basis upon which, if you're watching Netflix, if you watch a movie, Netflix will say, oh, these other movies are also recommended because they are similar to what you watched. They are similar to the outcome you experienced. And so we recommend those ones. So in other words, if I'm saying that there is a relationship between drinking of soft drinks and obesity, I expect that there will be a relationship between drinking of soft drinks and elevated levels of HbA1c. I would expect that there will be a relationship between drinking of soft drinks and increased risk of diabetes, for example, because all of those things are clustered together, they're all related with the outcome, right? HbA1c is a biomarker of your blood sugar level. So of course, I would expect it to be very strange for you to say that drinking soft drinks increases your blood sugar level, but somehow has no impact on the HbA1c. That doesn't make any sense, So coherence simply means that there's if A is associated with Y, then we expect that A is also associated with the nephews or siblings of Y as well, because they all flow together. Consistency means that the same results have been seen in other studies, in other populations. I, however, put it down the ladder because research is not about democracy, and it's possible for us to be collectively wrong. Think of research in the day of Galileo, where everybody concluded at that time that the Earth was the middle of a solar system, including very, very renowned, scholars like Aristotle, right? Everybody agreed that no, the Earth is the center of a solar system. And when Galileo came and said, no, I do not agree, it was like, no, you are a heretic. And so the fact that everybody agrees on something doesn't mean that it's true. And that's why I put it down in my ladder here. Specificity means that exposure A causes outcome Y and nothing else, right? And so in the case, and this is the core framework in Koch's postulates that, if we have all these people who have the disease, we should be able to isolate the microorganism in all of them. I put it down the ladder here because in chronic disease issues, you might not necessarily have that kind of specificity all the time. Analogy is saying that relationship between A and Y should be this way because there's another relationship that is similar to them that is also true, right? So if I'm saying, for example, I'm trying to measure the relationship between, quitting smoking and weight gain, I can say I expect that to be a strong positive relationship because I know that other studies have shown that lowered metabolism also has an association with increased weight. And I expect that to hold in this case too, because when you stop smoking, you have reduced metabolism. And so I expect those two relationships to go together. So analogy simply means that you have an example that you can compare that with. Of all of the Hill's criteria, in my opinion, the weakest is plausibility or biologic plausibility. What he is saying is that it makes sense to us that this should occur this way. In other words, it makes sense to us that if you drink a lot of soda, it should increase your weight. It just makes sense biologically. The problem with that is that when you say something makes sense to you, that is because you are basing that on what you know. But how much do you really know? That's the question, right? And because collectively, all the body of knowledge we have is almost negligible compared to all the things that we could ever know. So that's the problem I have with plausibility, because you are basing it on things you already know, which is a small fraction of the entire body of knowledge. So plausibility is a very dangerous concept because, well, that's the point for which we do research, to figure out the things we don't know. If we already knew them, then there will be no need for research. And so that's why I framed that last. And so you can think of, in this case here, how that will apply for the relationship between smoking cessation and weight gain. Now, we use Hill's criteria a lot in public health. I've reviewed a lot of Surgeon General's reports where we make a lot of causal statements. And the framework which we use in most of this, evaluations of evidence is Hill's criteria, really. So in a Surgeon General's report like this, we might come out and say the burden of death and disease from tobacco use in the US is overwhelmingly cost. See, I put the word cost there. How do we make those conclusions? This is the exact framework we use. We use Hill's criteria in the Surgeon General's report to make those kinds of statements. We'll look at the body of evidence and we'll look at, okay, how does this apply in terms of temporality and strength of association and consistency and the biologic gradient and plausibility and coherence. We look at all of these things and we'll say, all right, based on these things, there's enough evidence to say that A causes B or A causes Y. So to be clear, we're not sitting down and fitting some causal models and saying, looking at counterfactuals. That is not how we do it. We use Hill's criteria that we don't, again, we don't just use it as a checklist and we say, oh, there's consistency, no. It's not like a checklist. We really synthesize the evidence. We gather the evidence into spreadsheets with hundreds or thousands of evidence, and we then synthesize it as an expert panel and then make those decisions and say, based on the evidence available to us, using Hill's criteria, there's sufficient evidence to conclude that A causes Y. And that's how we do it. The next framework we want to discuss is Rothman's pies. Rothman is a professor of epidemiology in Boston University. I'm tickled by him because he's a dentist. It's not a lot of time we have dentists who are like, cutting edge epidemiology. So that's why I love Rothman. So Rothman came up with this framework that here is another way we can think of causality. Let's think of them in the context of sufficient causes. So sufficient causes simply means that imagine 5 people came to you with obesity. Well, the reasons why all 5 of them have obesity might be very different, right? So we can put the different reasons into buckets, which we can call sufficient causes. So maybe Mr. A had obesity because he has a genetic predisposition to obesity, and he does not exercise, and he does not do this, and he does not do that. The second set of people, their condition may be quite different, but they all end up with the same thing, right? So this is what Rothman is saying. Rothman is saying that let's put the unique set of conditions that can give rise to disease, let's call them sufficient causes. So in this case, for example, there are 4 sufficient causes for which an individual can have that outcome. The first sufficient cause is made up of factors A, B, C, D, and E. The second sufficient cause, which is a set of conditions, is made up of A, B, F, G, and H. The third is J, I, F, C, and A. And the fourth is just A. So what we're saying is that each of these sufficient causes can cause disease in of itself. So if we have this set of conditions here, that is enough to cause disease. If we have this one, again, that is enough. Now, so that is the idea behind sufficient causes. Now, let's introduce another term here. We talk about factors that are necessary. A necessary factor is a factor that appears in all the sufficient causes. So if you look at sufficient cause 1, sufficient cause 2, cause 3, and cause 4, what factor appears in all of them? Any answer?
A.
No. So exactly. So A. So it's A. So we say that in this case, we say A is a sufficient, it's a necessary factor. It's necessary because you have it in all the sufficient causes, right? So A is necessary. Now you can have a factor that is necessary but not sufficient. Remember, for it to be sufficient, that means that in of itself, it can cause the disease. Now, if you look at this sufficient cause 4, A is alone by itself, and A is still sufficient to cause the disease. So in this case, we say that A is both necessary and sufficient, right? So A is a necessary factor and it's also sufficient in of itself to cause disease. I hope that makes sense. Now, let's go to this next question here. Which factor is necessary in this case now? Which factor is, which letter of the alphabet is necessary?
Still getting A.
That's correct. Is there any factor that is sufficient in of itself?
So we also have C.
No, there's no C.
No.
Sufficient, the second set of conditions does not have C. So that means that you can have the disease without C. So that means that C is neither necessary nor sufficient.
Okay.
So for it to be necessary, it must be present in all the causal pies. So which one is necessary?
I think we still have A.
A is necessary. Now, in the previous example, A was necessary and A was sufficient. Now, is A sufficient?
No.
No, A is no longer sufficient because now A is no longer alone here in this sufficient cause 4. You have A and C. So in this case, A is necessary, but A is not sufficient. I hope that difference is clear. Let me see if there are questions here. Alrighty. I think that's none. Now let's look at our question, right? The smoking cessation question. Here we have 3 sufficient causes. Sufficient cause 1, 2, and 3. Sufficient cause 1, you have diet, which is blue. You have unknown because there's something we just don't know why an individual has the condition. Then you have smoking cessation here. And then the purple is genetic factors. So in regards to our question, how would you describe smoking cessation regarding its effect on weight gain? Would you say it is necessary? That's a question for you. Is smoking cessation?
No.
Okay.
Yes.
Okay, those who answered
Not necessary and not sufficient. Sufficient but not necessary. Neither necessary nor sufficient.
Sorry, let me correct that quickly. There's no way you can have something that is sufficient but not necessary. Sufficient is the whole set of conditions that are needed. All right. If it's sufficient, then that means it's necessary. I hope that is clear. So this is sufficient cause 1, sufficient cause 2, sufficient cause 3. Smoking cessation is not necessary and it's definitely not sufficient. If it's not necessary, that means that it's not sufficient, right? Because we see it appears only in this first set of conditions, right? And think of it, right? All the people who are, all of us who are overweight, is it because we quit smoking? No. Some of us are overweight because of other reasons. So it's possible that quitting smoking may be part of a sufficient cause in a particular model, but not necessarily in others. So in this case, smoking cessation is definitely not necessary and it's definitely not sufficient. So that's how we use causal pies in epidemiology. It allows you to just visualize things that are necessary, whether they are necessary and sufficient, or whether they're necessary but not sufficient. Any questions on that before we move on?
No question on this.
Okay, all right, great. All right, now let's look at the third way. Now the third way of exploring causal relationship is through regression models. So we now talk about how do we fit regression models that look at issues of causality and make those kind of conclusions. Now, let me make a distinction between causality and correlation. This is the population of interest we have. We have the white part is the treated, and the gray part is untreated. When we're looking at associations, we are comparing those who were treated versus those who were not treated. That's what we're doing. In causality, remember we said at the beginning that in causality, we are not looking only at observed outcomes. We are interested also in counterfactual outcomes. So what do? We now say, all right, what we're interested in comparing the outcome if everybody had been treated versus if everybody had not been treated. So now you see how we employ counterfactual theory in causal inferences. It's not just comparing people who were treated versus those who were treated. No, we are actually comparing if the whole population had been treated versus if the whole population had not been treated. Of course, not everybody was treated. So that's why we're saying again that causal models go beyond just the observed outcomes. We are creating or recreating a hypothetical scenario where everybody is treated and everybody is not treated. And we're now comparing the outcome if everybody were treated versus if everybody had not been treated. So this is the basis of what we call counterfactual theory in causal inferences. I'm going to stop there and see if you have any questions about the slide before I move on. Okay, no questions. That's fine.
Not this slide, but someone asked, how do you plot causal pi in a study? Is it by using odds ratio or risk ratio?
No, you use your knowledge.
And I think they also...
Okay, go ahead.
And then they're also asking if you could repeat the previous slide.
Okay, let's go ahead. You know what? Let me just run through the rest of the slides, and then I'll go back and answer your questions. How about that? Let's just finish the model so that we know we're done with the regression analysis.
Okay.
All right. So I'm happy this slide is clear. So the next few slides I'll present some of how that means in the regression so that it's clear to you. Just to understand some notations, whenever you start seeing superscripts in an equation, that should tell you immediately that we're talking about causal models. So you see superscript here. Once you see superscript, you automatically know that we're in the world of causality now. So here we are saying that the expected outcome y, a equals 1, remember a is the outcome, a is the exposure, y is the outcome, and c is covariate. So here we're saying that the expected outcome, if everybody had been exposed, which is a equals 1, minus the expected value, if everybody had been unexposed. Note that c equals 0 is here and c equals 0 here, meaning that in both cases, we are saying that we are holding a covariate constant. There's no difference between c and there's no difference between c here. The only difference that exists here is between the exposure. Here we have exposure of 1 and here we have exposure of 0. The bottom line, what you need to know here, just don't get to worry about the equation, is that number one, whenever you see superscript, we're talking about causal inferences, right? And here we're looking at the outcome if everybody had been exposed versus if nobody had been exposed. That is essentially what this small case A is saying. When we use small letters, like in this case, small letter A equals 1, it means everybody is exposed. If we had used an uppercase A, that means we're saying only among those who were exposed. So let me go back to that figure. So here we use, in these cases, we use big case A here. A equals 1, A equals 0. This is uppercase A to tell us that this is what they were actually exposed to. When we're talking about counterfactuals, we use lowercase. So you see, A equals 1, which is lowercase, meaning that everybody is exposed. A equals 0, small case, means everybody is not exposed, right? So you have to mind your sentence case when you are switching into the world of causal inferences. So contrast that to associations here. If we are saying the same thing here in associations, we'll say the expected value of y, given that A equals 1, if you were exposed, minus the expected value of y if you were not exposed. Again, in this case, we're comparing just this part. People who were exposed versus people who were not exposed. Causal, we're saying everybody if they were exposed and everybody if they were not exposed. Okay, let me just keep some of those complexities. And let's just talk about the assumptions for causal inferences, because you really need to understand this. This is the crux of causal inferences. Now, the good news is that these assumptions are more philosophical assumptions, but it's good for you to know them because that's the whole bedrock on which we make causal inferences. So the first one is that you have well-defined interventions. So that means that you have, in this case, the individual quit smoking or they did not quit smoking. So it's very clear. It's easy to identify who quits and who did not quit. And there is no misclassification or measurement error from that. That is pretty straightforward. Exchangeability is saying that the treated and the untreated are exchangeable. Another way of saying that is to say the outcomes in the treated will have been like those in the untreated if they had been untreated. So remember that we have some people who were treated, right? We're saying that their outcomes would have been exactly like the untreated group if those treated people had been untreated. And vice versa, the untreated would have been like the treated if they had been treated. Sounds like a tongue tie, but I hope you understand the basics. We're saying that those people the two groups are identical. The only thing that is separating them is treatment. So that if you, in other words, right, let's simplify it this way. Imagine if you had two people who are identical. One is a rich person, the other one is a beggar. We're saying that beggar would have been exactly like the rich guy if he had come from that same circumstances like the rich guy. And that rich guy would have been like the beggar if he had the same circumstances like the beggar. That's what we're saying, right? So they are exactly the same. The only thing that differs between the two of them is their backgrounds. And, that is what we're saying in exchangeability, that the treated and the untreated are exchangeable, meaning that the outcomes in the treated would be like the untreated if they had been untreated, and vice versa. So you see, the only thing that is different between in this equation here is that here you have A and here you have A prime. Everything is the same. Y equals Y, X equals X, everything is the same. So we're saying that the only thing that differs between the treated and the untreated is treatment. Another assumption that we have for causal inferences is positivity. Positivity means that I was struggling because our graphic designer, when he made the slides, he put a figure of a smiley face here as the icon for positivity. I had a good laugh at that. Positivity, it doesn't mean like being positive in life. It means that, in every group, the probability of, so let me explain it simply now. It means that if we take any group of individual, the probability of being assigned any arm of treatment is positive, meaning that it's greater than 0. So it must lie between 0 and 1, excluding 0 and excluding 1. So it means, let's even dumbify it even further, right? It means if you take any subgroup, that subgroup must have a mixture of both the exposed and non-exposed. So it doesn't matter what subgroup you take. Let's say you took men. Among men, we must have both people who are exposed and people who are not exposed. If you only have people who are only exposed among men, that means that assumption of positivity is violated. If you took, so any subgroup we took men aged 50 years or older. In that subgroup, we must have people who are both exposed and non-exposed. So the probability of being exposed must be positive, and the probability of being non-exposed must also be positive. If the probability is 0 or 1, that means that we have violated the assumption of positivity. So that's what this assumption is saying. Consistency is saying that we expect that the counterfactual outcome, that the observed outcome aligns with the counterfactual. So the case of Mary took the pill and died. We expect that if Mary did not take the pill, Mary would not have died. So that there's an alignment between the observed outcome and the counterfactual outcome. And then the model should not be misspecified. So that means that we should use the correct model. To simplify, to illustrate that here, remember we said in one of our previous classes, we explained what the model is. A model is just a simplification of reality. It is just a simple way we can explain reality to people. Imagine if you had somebody who had never seen an apple before, and you were supposed to draw an apple for them. This is the apple that you have in real life, and you're supposed to draw that apple. Which of these apples on the right here is the least misspecified? Which do you think? Remember that a model is just a way to simplify nature and to explain nature to somebody who, since we don't have the actual data, right? That's what a model is. So we're saying that you must not misspecify your model. So to make that intuitive, I'm asking, which of these models is the least misspecified relative to reality here?
Number 4, the red one, none.
So let's call this 1, 2, 3, and 4. So 1, 2, 3, 4. So which model is least misspecified?
4, 2, 1, 4.
This one
Mostly
is least
4.
specified. This one is half 18.
Yes.
Do you mean most misspecified? This is the one that is least misspecified, right? Because it looks, in the shape, it looks like it. See, it has a flower. It looks like this. So if I show a picture of this to somebody, I can say, oh, I see it. So the stuff is red and it's roundish and it has a leaf. This one is kind of misspecified because I show this picture, somebody is like, so apples are black and white. That's his conclusion, right? So this model is misspecified. This one, it looks like this, but it's misspecified in the color, right? I show him this was the reality. The reality was this particular apple. This is not what we're seeing here. The shape looks the same, but the color is different. This one has a lot of missing data, right? And so if it has a lot of missing data, then it's misspecified because it's not really capturing what we are seeing in reality. So this is essentially what we mean by misspecification, right? You want to make sure that you don't make incorrect assumptions, that there's no extensive missing values, that the model actually captures the reality. If the relationship is linear, then you should specify a linear fit in the model. If it is quadratic, you want to specify a quadratic. That's like saying that the apple is green, but you specify the red color. You should specify the relationships that are actually observed in nature. That is what we mean by model misspecification. Now, let me now show you quickly how we fit the models so that you can see how all of that comes together. So this is data from Enhance. Enhance is the National Health and Nutrition Examination Survey of adults aged, in this case, 25 years or older. We had the baseline survey in 1971 to 1975, and then there was a follow-up in 1982, right? The survey collected data on various, measurements like your height and your weight and all of those things. And then the analytic sample in this study, analysis included 1,556 cigarette smokers who completed both the baseline and the first follow-up survey. So again, the question we're trying to answer is quitting smoking associated with weight gain? Remember, that's the question. Quitting smoking in the data set is a variable called QSMQ, quit smoke. That means that you smoked at baseline, but you did not smoke at follow-up. Then we have another variable called weight change. The weight change is the difference in weight between 1982, which was a follow-up, and 1971, which was a baseline. And then these are the potential confounders that were assessed: age, sex, race, ethnicity, education, physical activity, smoking intensity, and smoking duration in years. Our goal is to fit a causal model. Remember that if we're fitting an associational regression, all we need to do is compare individuals who have quit smoking with those who have not quit smoking. And we can say the mean weight gain was 5 pounds higher among this group compared to that group. That's how we talk about associations. That is not what we are trying to do here. We're trying to fit the counterfactual model. In other words, we're trying to say, what would be the difference in weight if everybody had quit smoking versus nobody had quit smoking, controlling for all the confounders? That's why we have C equals 0, right? We're saying we're keeping the confounders constant. We are eliminating them. That's why we have C equals 0 here and C equals 0. So how we're going to do this? I mean, we have only one data set where some people were exposed and others were not exposed. So what are we going to do? Well, the first thing is that we're going to create 3 copies of the data sets. The first copy will be the original data set. The second and third copies will create counterfactual scenarios where everybody is exposed versus nobody is exposed, right? Now, let me just walk through that. So this is the data set we have. This is the ID of the individuals. This is confounder 1. This is confounder 2. This is the exposure variable, and this is the outcome variable. So this is the data set we have, simplified, obviously. What we're going to do is we're going to create copies, 2 copies of the data set. So this is copy number 1. This is copy number 2. You can see that this is exactly the same in, everything is exactly the same in these copies as the original. We have created a new variable here called duplicate. So you have the duplicate has a value of 0 if it's the original data set. This is the first duplicate, and this is the second duplicate. So our data set is now has 3 times more rows than we had in the original master data set. Now, the next step we're going to do is that we're going to take the first copy and replace everybody from being, we're going to assign all of them as being exposed. So you see the exposure here. This is what we had. We're going to change everybody in this second data set to become exposed. In the second copy, we're going to change everybody to become non-exposed. And then we're going to put the missing values here. We're going to put missing values to the outcome column here, right? For both the first and second copies, right? Because obviously we have not seen the outcome yet. We did not measure the outcome when everybody was exposed or everybody was non-exposed. That is what we're trying to capture counterfactually. So far, so good. I hope you guys are still following me. Any questions so far? All right, no question. All right, good. Now, next, we're going to fit the regression model. We're going to fit the regression model based on the whole data set. Now, one of the things you should know is that when you fit the data set with that has missing values on any of the covariates used in the model, the regression model does what we call list-wise deletion. It removes every row that has missing value from the data set, from the analysis. So even though we're using the whole data set to do our regression analysis, since the outcome has missing values in this column for the both duplicates, this duplicate will not be included in the regression, right? It will be only the original data sets that will be used in the regression. So we do our regression, and then what we then do next is that we create predicted values. Prediction is what we sometimes do after you fitted the regression model. We're now saying, okay, we fitted the regression model. Now, let us predict the expected value of the outcome based on these conditions. So here, when we say, given the predicted value of the outcome, is saying, okay, here's a predicted value, assuming that this individual has exposure value of 1 and has this confounder and has this value. And so the prediction is going to apply to the whole data set, right? It is not just to the original data set. So that is now, we've now successfully been able to now predict the mean values if everybody, for all the second data set where everybody is exposed, as well as in the second data set where everybody is non-exposed. So again, I'll recap. We take the original data set, we create 2 extra copies. We create the hypothetical scenarios where everybody's exposed and everybody's non-exposed. We fit our regression model with the appended data sets. But of course, since regression will do a list-wise deletion, the regression itself is done only with the original data set. But when we predict the outcome, it is predicted for everybody, including those in the duplicated data sets, right? Then we can then then the next thing is just saying, okay, what's the average value of the weight in the predicted weight minus the average weight in the predicted for the exposed. So exposed minus non-exposed. So we now come back to this scenario here where we're saying, what is the expected value of y when everybody is exposed minus the expected value of y when everybody is not exposed? That is how we come back. That's how we solve this causal equation, right? Because we now have a data set where everybody is exposed and everybody is not exposed. So in that case, we now restrict our analysis to just copy number 1 and copy number 2 with the predictions. So it's going to be the average value here where everybody is exposed minus the average value here where everybody is not exposed, and that gives us the average causal effect. That is what causal, models are in a nutshell. But I'm more focused on you understanding it at least conceptually than with the code. I'm going to explain the code in a bit, but this is the more important part where you can now just in a very, very simple way see what is happening behind the scenes in all these complex regression models that have been fitted of a causal nature. That is all we're doing. So let's look at what I just described in code now. There's code in this slide for theta and for R. So here I am creating 3 copies of the data set. This is y all. This is the original file. So y unexposed is equal to y exposed equals y, right? And then I append all the 3 data sets together. So y is equal to R bind, y all, y unexposed, and y exposed. So I have appended all 3 of them together. This is this part here. This is what I have done here now. This is this part here. I created a duplicate and then I appended them together stack by stack. So this is this first step here. And then second step here is to replace everybody in the first duplicate as exposed. So I'm saying here that replace Q smoke, which is the exposure, as 1 if the duplicate is 1. Remember, duplicate 1 is this first copy. So I'm saying assign everybody here a value of 1, and then assign everybody in duplicate 2 a value of 0. That's what I'm doing in this code here. So I'm saying take duplicate 1, and for the variable quit smoke, assign everybody a value of 1, and then take that same data set for where you have duplicate equals 0, and assign everybody a value of 0, right, for that same variable. And then I'm saying, well, for the outcomes, assign both the duplicate 1 and duplicate 2 values of missing values. That's what I'm doing here next. So I say, replace the weight gain or weight difference between the 2 waves, a value of NA if duplicate is either 0 or 1, right? So I'm saying take the 2 duplicates and assign them values of missing values for both the duplicate 1 and duplicate number 2. That's what that code is doing. And then step number 3, I'm now fitting a regression model. Using a generalized linear model. This is the outcome here as a function of quit smoke, which is a predictor, and the confounders, which is smoke years. Now you can see smoke years is a continuous variable. I don't want to have any model misspecification. So for all the continuous variable, I'm expressing them as quadratic, right? If the variable was originally linear and I captured as a quadratic form, that is still fine, right? However, if the variable was quadratic in the real world and I captured it as a linear variable, I have a problem because I have just misspecified that variable. Going back to the issue of the apple we talked about, right? If it's red, don't say it's green. If it's quadratic, don't say it's linear, right? So for all the continuous variables here, I have just expressed them as quadratic just to ensure that I'm not misspecifying the variable. So all I'm doing here is fitting the regression model with my data set Y. So I'm using this entire data set, right? But remember that since it's enforcing list-wise deletion, it's going to restrict the analysis to only the master file. These guys have missing values for copy 1 and copy 2, so they will not be used in the regression. So after fitting my regression, next, I will now generate predicted means, the predicted values of the outcome conditional on the covariates. So that's why I'm saying, give me a column called mean Y and calculate it by predicting the value of y from the regression model, the outcome, which is the response. So I'm saying that give me this new column here by predicting the outcome that we'll have observed based on the covariates. So that is where I get all of these numbers from, right? And then the next step is just to now see what is now the average causal effect of quitting smoking on weight gain. It's just simply saying, take the mean of the, of the predicted values where everybody's a smoker, everybody quit smoking, and subtract that from the average of the predicted values where nobody quit smoking, right? So again, remember that for counterfactual outcomes, we are not interested in comparing exposed versus unexposed. We are comparing if everybody in the population had quit or everybody was exposed versus if nobody was exposed. And that gives us the value of 3.461. So that means that this is the average causal effect. So this is the same state. I'm not going to go over it. So how do we interpret this? We have a value of 3.46. If this was an association, how will we interpret it versus if it's a causal model, how do we interpret it? If this was an association, we will say individuals who quit smoking had a mean body increase of 3.46 kilogram compared to those who did not quit smoking. That's how we will frame it. However, for causal models, it's quite different. We will say the difference in mean body weight if everybody quit smoking versus if nobody quit smoking across the study period is 3.46 kilogram. Or you can say the average causal effect of quitting smoking on mean body weight is 3.46 kilograms. So that's how the interpretation of causal models is quite different from that of associational models. All right, and I'll stop here and take any questions that you have. I know this is quite a new topic. So again, the goal is not for you to become experts in causal inferences. It's just to introduce you gently to the concept of causal theory and how we do it. I mean, it's a bit more complicated, but I've just tried to really dumbify it so that you can just understand the crux of the whole issue and at least have a good understanding of how it's done. So questions?
So the predicted values, Dr. Agaku, how did you arrive there?
You just write a code.
Was there a formula?
No, you predict from your regression. You use your software. You can only predict if you have fit a regression model. The whole point of regression is to generate predictions. That's why we do regression. We regress so that we can generate predictions. That's so you can get that from the code. You write that in your code. In this case here, let me go back to my code. Hope you can see my screen. So here you see mean of y equals predict. So in R, for example, there's a command called predict. For you to predict, that means that you must have fitted the regression. So my regression was called model 1. So you can see, I first of all fit model 1. Mod 1 equals GLM, and so on and so forth. And then I now say, generate a new variable called mean y, and generate that variable by predicting, right? Using model 1, you can only predict from a model you have fitted. So I fit the model first, and then I run predictions based on that model, right? And this data set, and using the outcome. So that's how you predict.
Okay. Can we have the code for Stata? And which software do you recommend for DAG?
You don't have to use software for DAG. You can draw it by your hand. So that's why you have to understand the relationships clearly. I mean, there are lots of software for DAGs, don't get me wrong, but I feel they're completely unnecessary because it should be driven by subject matter knowledge. So a DAG is not something I will relegate to a software to create for me. I really want to sit down with my tablet or with my pen and paper and actually draw DAGs by myself. So yeah, but if you feel comfortable with the software, you can, but it's not something I would recommend. It's one of those things that you should really do by hand.
More explanation on interpretation.
Okay. Let's go back to interpret. Let's go back to this. This slide is fundamental to your understanding of how to interpret causal models. So see, in association, we're comparing this guys here versus this guys here. We're saying the people who were exposed compared to those who were not exposed. This is what we do in associations. For causation, we are saying if everybody had been exposed versus if nobody had been exposed, this will have been the difference. So this is, you have to just understand this figure, this output, to understand the difference in how we interpret associations versus causation.
How do we determine the counterfactual outcome?
It's implied. If you say, if your study is, for example, factors associated with, let's say you're looking at, is there a relationship between parental smoking and youth smoking? Well, the observed outcome of interest is, there are only two observed outcomes, right? The youth smoked or the youth did not smoke. These are the exact same counterfactual. The youth smoked or the youth did not smoke. It's only that you can only have one of those two outcomes observed. You can't smoke and not smoke at the same time. It's either you smoked or you did not smoke. Now, the opposite of whatever you had observed is now your counterfactual. So if I smoked, my counterfactual outcome is that I did not smoke. Or if I did not smoke, my counterfactual is I smoked. So the observed outcomes and the counterfactual outcomes in terms of their sets are the same. If your outcome is, you're pregnant or not pregnant, well, these are the same counterfactual outcomes. But for any given individual, you can only have one observed outcome, and the other outcome automatically will become your counterfactual outcome.
Is correlation equal to association?
Yes, roughly.
May I know why you put smokers squared in the model? That's I. Smokers squared in the model.
Smokers squared in the model. I'm trying to understand what that question is saying. Unfortunately, I don't have the context for that. I'm trying to see. Let me see if I can, where that question might have come up. Is that question coming up from the code or from the equations?
Fabrice, please explain. Okay, in the meantime, another question. In terms of counterfactual, if Mary did not take the medication, she may still have died. So the counterfactual outcome may really be difficult to say. Is that correct?
That is correct. But we also, that's why I said earlier that the assumptions are more philosophical. There are things that we want to believe in. Like if Mary took the pill and Mary died, then remember one of the assumptions of causal inference is consistency. Consistency means that we are now in a real pickle if Mary took the pill and died, and if Mary did not take the pill, she would still have died counterfactual. It's like, that is not adding up. We're having contradictions in our observed and counterfactual outcomes. So that's why we say that for consistency, if Mary took the pill and died, then we want to believe that if Mary did not take the pill, Mary would not have died. Again, you have to remember that these are all philosophical assumptions. We're saying that this result is valid if all those assumptions held true. Now, you know what they say about models, right? All models are false, some are useful. So that's a framework you have to think about these things. Nobody's saying that this is the absolute truth. It's just saying that this is one way we think about the world. This is one way we think about outcomes and how we can measure them, right? So it's not, nobody is even remotely suggesting that, yeah, this is the word of God or this is the definitive truth. Remember, all models are false, some are useful. So that's the framework you have to approach these things.
What is the difference between correlation and logistic regression?
Logistic regression is a type of regression model. Correlation is just a way of measuring relationships. You can measure correlation association using a regression analysis, but there are other ways you can do it. So it's the comparison is a bit abstract. The two things you're asking for are not like they're not apples, they're apples and oranges because they're quite different. Regression analysis is like a tool we use to measure things, right? Whereas correlation is more of a we're saying that when you have two things, is there a relationship between them, right? So we start by saying, is there a relationship between A and B? We say, yes, there's a relationship between them. The next question is, how do we measure that relationship? You can then say, oh, let's use a regression analysis. Let's use logistic regression. Let's use linear regression. So you're only using the tool to measure a relationship. I hope that makes sense. So that's how they're related. You first ask, is there a relationship? Yes or no? If there is, how do we measure it? The logistic regression or all regression models are just giving us a tool with which you can use to measure relationships.
Does counterfactual relate to the exposure or only the outcome?
Counterfactual is talking about the outcome. Counterfactual outcomes. There's, of course, the issue of consistency means that we're saying we're not looking at the counterfactual outcomes in isolation. We're saying there's a link with exposure, right? So we're saying, okay, if Mary took the pill is the exposure, and died, which is the outcome, then, if she did not take the pill, she should not die. So we always talk about these things, exposure and outcome. But strictly speaking, counterfactuals is referring to the outcomes.
Toyosi, you may unmute yourself and speak. Toyosi, you have a question?
No, it's been attended to.
Oh, okay. Your hand was still up. All right. So back to Fabris. It's from the code, the squared. From the code, GLM equals.
Okay. Okay, so so here, right? So I'm assuming this is what you're referring to here. So here, okay, okay, I guess you're talking about here, weight 71. Can you confirm so I'm explaining the right thing?
Fabris, please confirm. Yes.
Okay. So in this model, right, we are adjusting for smoking years, how long you've smoked, smoking intensity, whether you exercise or not, your level of education, your race, your sex, your age. Age is continuous. That's why we have both a linear and we have a quadratic form in it, because we want to avoid model misspecification. And we're also adjusting for baseline weight. Like if you were fat at baseline, well, not surprisingly, you would fat at a follow-up, right? So, but we're not interested in your baseline weight. We're talking about the change in weight from baseline to follow-up. So what we're doing here is that we're also adjusting for your baseline weight, which is a continuous variable. And so we want to avoid model misspecification. So we also include a quadratic term here. So that if again, remember what I said earlier, if a relationship in the real world is linear and we use a linear model, we are fine. If it's linear and we use a quadratic model, we are still fine. However, if the relationship is quadratic in nature, then we use a linear model, that is completely false. We have misspecified that model. And remember that one of the assumptions for causal inference is no model misspecification, right? You cannot have incorrect assumptions. Like you cannot assume that a relationship was linear when indeed it is curvilinear or quadratic, right? It is like saying that, oh, the apple is red, but we're painting it green. So that is why, so there are two parts to your question. Why do we have quit smoke in a model? Why do we have the baseline weight? Well, we have the baseline weight because we want to adjust for the baseline weight, because what we're interested in is what happened in the period of follow-up, the period between the baseline and the follow-up, not necessarily in the baseline. So we adjust for baseline weight because the baseline weight obviously predicts any loss or gain in weight at follow-up. So we hold that one constant, and because it is a continuous variable and we don't want to misspecify the model, we include a quadratic term just in case the relationship in nature was quadratic. I hope that is clear.
Yes.
Okay.
Joseph. You can ask your question. Please unmute. Joseph, your hand is up. Okay. Do we have any other questions? No. All right. It seems there are no more questions.
Okay. I hope you guys were not thoroughly confused. I tried to make it as simple as possible, but I concede that this could be quite an abstract topic. It is, no, it could be. See, I didn't want to make this topic. You guys insisted that, oh, you want to hear about causal inferences. Be careful what you wish for. I tried to steer you away from this, right? But you were like quite adamant that you wanted to hear about causal inferences.
They say you did great.
Oh, thank you.
Very grateful. So do you want to tell us about village school since we don't have questions?
No, please, you go ahead. Yeah.
This is about the presentation. We're doing a lot of things. Okay, so from next Thursday, we invite PhD students, master's students, or any student, if you are maybe about to, well, at any level of your studies. It could be that you are still preparing your proposal, or you are about to submit to ethics, or your study has been approved, whichever way. So we want people who can present, and we have our first presenter for next Thursday, but we plan to continue with this every Thursday. And we want people we will share a template. I'll also share via email the flyer so that you can register if you want to present to us. And Dr. Gaku will be there, obviously. He will provide guidance. You will be grilled, he said. So you must be up for a challenge. So if you have any questions, you can always ask. But for the presentations, we also would like you to invite your supervisor, from your school to be there, just so they can also be part of the whole presentation and also be able to provide guidance, or just make it more interactive. So you can also invite your classmates, and we just have a good time while you improve your study, well, your methods or protocol. Okay, chorus. All right. Okay, so I hope you got that. But I'll share that information also via email when I send the recordings. And you will also receive certificates, since this is the last session from the state bootcamp. So Dr. Gaku, can you explain chorus?
No, please go ahead. I'm taking a break from talking about counterfactuals. Try talking about counterfactual theory for 2 hours and then let me know what I can talk about any other thing.
Oh, wow. Okay.
I feel I've been
But
traumatized.
you speak so well, it doesn't seem like it takes
Oh,
any
really?
effort.
Okay.
Yeah.
Next time we have a class on causal inferences, how about you present it?
Well, I have not read that textbook 10 times like you did, the epidemiology stuff. So I would not know how to explain the things the way that you do. So anyway, about chorus. Chorus is the first cycle of, the thing is I'm reading, Dr. Gaku, as you would talk about it much easier. So, but anyway.
How come you're not even on video, Lungile?
Okay, just a second. Yeah, today I'm here to support you. Joseph, your hand is still up. I don't know if you know this. Let me stop the